let me just see. Do you want to say anything, or you want to?
I think you can know James as well as anybody.
Okay. All right, take it away.
We're good to go. You're good to go.
All right, thank you for coming. Good afternoon, everybody. This is, you know this already, but I'll say it. This is James Anheuser's Ph.D. defense. My name is Jeff Key. For those who don't know, probably most of you don't know that. I'm one of the NOAA people in this building, and so you're probably wondering, why am I standing here? Well, Tristan Lequier is James's academic advisor, but I and Yingwei Liu, another NOAA person in this building, supported James for this work on a NOAA grant. We also provided scientific advice to the extent that he would listen to us. Anyway, a little bit of background on James. He did his bachelor's degree here at UW-Madison in mechanical engineering, not in atmospheric sciences, back in 2012. Then went into the private sector, worked for 6 years, designing equipment, designing parts for agricultural equipment and construction. Then came back here to AOS and did a master's degree with Elizabeth Weiss, who is not here. It had to do with data fusion of polar orbiting, sounder data with geostationary imager data. Then in early 2020, after finishing his master's degree, he came to work with Yingwei and I and the cryosphere group. And at the time, we weren't sure exactly what he would be doing. We do remote sensing of polar regions, sea ice, clouds, not so much clouds now, but a little bit of cloud, surface radiation, and so forth, but a lot of snow and ice work. And I came up with a great topic, which has to do with what I consider the holy grail of satellite remote sensing in the polar regions, which is sea ice thickness. Sea ice thickness being, again, I think, the most important variable. All we ever hear about is sea ice extent, sea ice area, but if you think about it, sea ice thickness in the limit of 0 means no ice. So if you have sea ice thickness, you have most of what you need for the thermodynamics. But he took it one step further and went into not just the thermodynamics of changes in sea ice, but also the dynamics, and that's what he's going to tell us about. And he's also going to tell us how well models are doing, and I won't spoil that. So take it away, James.
Great, thanks, Jeff. You took care of the motivation slides for me. That's wonderful. So, yeah, the title essentially, off of what Jeff was saying, thermodynamic versus dynamic sea ice thickness effects in observations and models. So, to take it a step further from what Jeff started talking about there, very timely, I have a slide here with a couple of plots. These are the CMIP6 models. They're monthly means from 1990 to 2009 showing sea ice area and sea ice mass. And in both of these plots we have a black line that shows a observational product for sea ice area and sea ice mass. And the first thing that you can see is a much more defined spread across the models in the sea ice area plot than we can see in the sea ice mass. The individual models here, color coding doesn't really matter for this particular purpose here, but you can see a nice, fairly coherent grouping of models in the sea ice area side of things. But the sea ice mass, which as Jeff mentioned is important, much more important thermodynamically, has a much wider range across the CMIP6 models for 1990 to 2009. I mean, on the low end we have in January 10 times 10 to the third gigatons of ice. On the high end, almost 30. So that's a significant difference across CMIP6 climate models, and that's something that we really want to try to get a handle on. Why is this happening, to build confidence in future projections of sea ice from these models? And one way to do that is to get down into the process level. So to do that, we'll be talking, throughout this talk, I'll be using a governing equation, which is really fairly straightforward. It's a change in CS thickness over time locally is equal to a thermodynamic effect and a dynamic effect. The thermodynamic effect here is the function F. That is a thickness change due to phase change, so freezing and melting. But that ice is floating and parcels are moving relative to one another, and that leads to a dynamic effect as well, whereby the ice can move in and out of a region, but also converge and diverge, thereby causing ridging, increasing thickness, or crack or fractures will form. We call that leading, reducing the sea ice thickness in that region. Like I said, the thermodynamics is this function F. It's a function of time, thickness, and location. And the dynamics is really just a calculus term. It's essentially compressible advection, the divergence of the flow field U times the thickness H. And these two effects are affected by different mechanisms in a changing climate. So really what we need to have are separate observations of these two processes in order to compare to models. But large-scale observations of these processes and their comparison to climate models are lacking. So this is the fundamental issue that I have tried to address through my PhD work. On to an overview of what we'll be seeing today. We saw the motivation and background. So to go after that fundamental issue from the last slide, I have 3 chapters. These numbers don't match what's in the document, but chapters 1, 2, and 3, thermodynamic, sea ice thickness growth rate, satellite retrieval. We'll use that in chapter 2 to determine what is the pattern of thermodynamic and dynamic sea ice effects in the Arctic. And in chapter 3, we will compare those patterns to global climate models and answer the question, how well do global climate models represent these thermodynamic and dynamic sea ice effects? I'll leave you with a summary and next steps at the end. Okay, chapter 1. This is published just this year, it should say 22, in the cryosphere, thermodynamic sea ice growth rate satellite retrieval. For this, we'll start with a one-dimensional sea ice growth model. Very simple schematic here. We have ocean, liquid water. We have sea ice floating on top, air and snow above that. And from a fundamental standpoint, ice growth occurs at the base of the ice. That growth releases latent heat. That latent heat, along with any heat flux that is being transferred from the liquid to the solid ice, then conducts up through the ice. So we have in this simple model, we have a one-way flow of energy whereby the ocean flux plus the latent heat equals the conduction. We put an energy balance at that solid-liquid interface, and then we have, as I said, latent heat of ice fusion plus ocean flux equals conduction upward. So in Stefan's law, that simple schematic is put into an equation where we have latent heat of fusion, which is density times latent heat times the change in thickness over time, is equal to conduction, which is just the simple heat equation, conduction, where you have a temperature difference across the ice between the freezing point at the base and the snow ice interface temperature TSI at the top, driving an exchange of a flow of heat via conductivity K, and finally ocean flux F sub W. And we have some assumptions here. We're neglecting horizontal conduction, we're neglecting thermal inertia, and we're neglecting internal heat sources. These assumptions are important. They allow this relationship to be an instantaneous relationship between this temperature in particular, snow ice interface temperature, and this growth rate, dH over dt. And you'll see why that is in the coming slides. So in Stefan's law, integrated conducted energy, or what I call SLICE, this is the retrieval methodology itself, we take a passive microwave retrieved snow ice interface temperature and directly put it into the solution to Stefan's law, which is shown here. I have green boxed the snow ice interface temperature just to further illustrate how this works. We have H, thickness H, equal to an initial thickness, and following the rest of the solution to that differential equation, we were able to get a final thickness H for a given time step here. So some attributes of this retrieval, it does indeed retrieve instantaneous thermodynamic growth. It has daily basin-wide coverage. And we've assumed a ocean flux value of 2 watts per meter squared in keeping with other modeling studies that have assumed a similar value. Some caveats to this: we do require an initial condition, H sub naught, in order to retrieve an absolute thickness. Big one here is this is not compatible with the melting season. This is growth season only, or sunlight. So this is going to be for winter only, and we require 95% or greater sea ice concentration because the open water, any open water, will interfere with the passive microwave signal, making this not work. So to show some results of SLICE, we'll use a buoy data set. So the U.S. Army Corps of Engineers Cold Regions Research and Engineering Lab, or CREL, runs a network of ice mass balance buoys in the Arctic that we will use as a ground truth to compare SLICE to. These buoys are Lagrangian in that they move with the ice pack. They're installed in the ice, as shown here in the graphic at right, and they float along with the ice parcels throughout the season, taking various forms of data, including ice thickness, which is what we'll be using. We're using all of the buoys from 2003 to 2016 that cover an entire growth season. That comes out to 10, excluding any landfast ice or obvious dynamic effects. We're using the passive microwave data from closest to the buoy location, and like I said, we're using buoy thickness and the daily mean and SLICE is applied daily. So here's the summation sort of the comparison. On the left we have the retrieve versus buoy snow ice interface temperature. This snow ice interface temperature retrieval was not novel to this work. This was something that we used from the literature, but useful to show how well it does. There's a very small bias of 0.05 Kelvin and a fairly decent linear correlation of 0.7 in that comparison. And that manifests in SLICE with, again, a fairly small bias of 0.0004 meters per day, which is about 10% of kind of the mean, the middle of the thermodynamic growth rate that SLICE is retrieving in the vertical versus the buoy in the horizontal. And again, a similar linear correlation of 0.7. So to round out the chapter here, our conclusions: SLICE links the passive microwave retrieved snow ice interface temperature to Stephan's law in order to retrieve daily basin-wide sea ice thermodynamic growth. And in a comparison to an ice mass balance buoy data set, there's a bias of 4 times 10 to the negative 4th meters per day in that comparison, and a linear correlation of 0.71. So fairly effective at retrieving thermodynamic growth rate. Okay, that concludes chapter 1. So now into chapter 2, which similarly is published as a preprint in the cryosphere. Again, that should be 22. Not sure why it says 21. Stuck in the past, I guess. In chapter 2, we'll ask the question: what is the pattern of thermodynamic and dynamic sea ice effects in the Arctic? And there are a couple of studies that have started to look into this. This is sort of a new line of inquiry to do this from an observational standpoint. The first being a study that used ICESat-2, which is a laser altimeter that's used to measure sea ice from space. They were using the ICESat-2 returns along the Mosaic sea ice, or the Mosaic drift observatory to determine what the thermodynamic and dynamic mix is. They found that the dynamic growth accounts for about 34% of the mean sea ice growth along the Mosaic drift observatory. I should say both of these studies, I've been saying Mosaic, we're measuring thermodynamics versus dynamics along the mosaic drift track. I don't remember what mosaic stands for, but it was a floating observatory in the winter of 2019 through 2020, measuring all sorts of various Arctic and cold weather variables along that drift track. And like I said, these two studies were investigating the thermodynamic versus dynamic growth along that drifting track. So I covered the first one. The second one, von Albedil from 2022, found thermodynamic growth as modeled with buoy temperatures and overall growth from airborne electromagnetic surveys. This study was on a smaller scale than the satellite scale that we have in the first study, but at that smaller scale, they found a smaller dynamic contribution of 10% than the 34% from this previous study. But what we sought to do is expand on these studies at a larger scale, both spatially and temporally. So in order to do that, we will return again to the governing equation, where we have thermodynamics and dynamics summing to a total change. And we've put in the cryosat-2 thickness. Cryosat-2 is a satellite altimeter similar to ISAT that measures overall sea ice thickness. So we'll get the overall sea ice thickness changes from cryosat-2. We'll use SLICE from chapter 1 to retrieve the thermodynamic effect, and then find the residual of those two terms to find dynamics. So the total change minus SLICE, minus the thermodynamic effect from SLICE, will be the dynamics as a residual. So the cryosat-2 product that I used for this is the Alfred Wegener Institute, or AVI, CS2 SMOS. It is a weekly combination sea ice product. It uses the cryosat-2 along with SMOS, which is a very low frequency microwave instrument that helps fill in some of the gaps with cryosat-2. Anyway, this weekly product, it covers 2010 through 2021, so that's how long our analysis here is for, and there's a reference there for more about that CS2 SMOS product. And what we can further do, looking at the math here from the dynamics term, this can be further factored. This calculus term can be further factored into an advection contribution and what we'll call a deformation contribution. So this first term, this is again the same governing equation, the same overall change, the same thermodynamic contribution, but focusing on the dynamics here, we've split it into two separate effects. First, advection, just how does the flow U change the overall thickness at a particular location. That's what we have in advection, just like you would think about advection in any other type of context from a meteorological standpoint. And then the second term, deformation, this is really where the convergence and divergence comes in. So to what extent is the ice converging and piling up and ridging and becoming thicker, or diverging, lead formation, fracturing, and becoming thinner? And so in order to do this, pretty straightforward. There's timings on these slides. I thought I took them off. We have the spatial gradient of the cryosat-2 field that we have, multiplied by the motion vector, just subbing in cryosat-2 for H, and then subbing in a satellite observed ice motion vector product in for U, and just calculating that, using these two fields, and then using again the residual for the deformation portion of this dynamics. So overall change from cryosat, thermodynamics from SLICE, the overall dynamics is a residual of that. Then we calculate the advection, and then further find deformation as the residual once again. And I've noted here that this the deformations can sort of be thought of as Lagrangian dynamics as well, because since we've taken the advection out of this term, what the deformation represents is what a drifting observer would notice due to dynamics. So if you were to be like a buoy or like the Mosaic drift station, you would not see the effects of advection because you as an observer will be riding along with the advection. So the deformation term you would experience as dynamics. So and I'm calling that Lagrangian dynamics as well. And that'll be important for comparison with the Mosaic studies that I referenced in the previous slide, just a little foreshadowing there. Okay, so now to the results of what we have here. So this slide shows the 2010 to 2021 wintertime mean for each of those four terms that we saw on the last slide: dynamics, thermodynamics, advection, and deformation, all on the same color scale with the ice motion vectors averaged over the same time period plotted alongside. I've shown here there are two sort of climatological sea ice motion patterns that dominate in the Arctic that help understand what we're seeing here. The first is the Beaufort gyre. Might be slightly difficult to see further back, but in this upper green circle we have sort of a circulation of ice motion. It's a gyre in that the ice is, along with the ocean current, moving sort of in a circulation in that region of the Arctic. And then we have the transpolar drift as well, the bottom green oval, where the ice motion is, rather than a circulation, it's sort of a straight sort of current, so to speak. Maybe that's the wrong word. A straight linear motion of the ice, predominantly from the regions north of Russia and Asia over towards Greenland. So these are climatological dominant motions of the sea ice that, again, help understand what we're looking at. So let's take those away now that we know what they are. So the first obvious point here is that in this region we have dynamics increasing sea ice thickness. And that's expected because both the gyre and the transpolar drift are pushing ice climatologically against the Canadian islands, the Canadian Arctic archipelago. And once, it's pretty simple, once the ice reaches those islands, it doesn't have anywhere to go anymore, so it ridges up upon itself. And this is a phenomenon that's not unexpected, but to be able to see this in some sort of observational context with a magnitude assigned was very exciting to see. It's sort of a new phenomenon. And we can also see just what's really interesting is also here in the Chukchi Sea, north of eastern Siberia, another smaller region of an increase in sea ice thickness. And it's exciting to look at this field and know that it was calculated without any input from the sea ice motion vectors. The advection and deformation fields involved the sea ice motion vectors, but this one did not. So to see that it, matches up with the ice motion vectors, rather the Canadian archipelago, and then in this region as well, where the Beaufort gyre is sort of leaving off some ice as it circulates around, which similarly ridges in this region and increases thickness. It's an exciting result to see. And then we see in these regions as well, where the transpolar drift is originating from, ice being removed from those coastal regions, therefore decreasing the thickness there. So on to the second one, B, thermodynamics. By the nature of the way that the physics works, we would expect to see higher growth in regions of thinner ice. I won't go all the way back, but in the relationship of sea ice growth, there's a thickness H in the denominator of the growth term. So it's inversely related to sea ice thickness. So we have, as expected, in the regions of thicker ice in the central Arctic, lower climatological thermodynamic growth, and higher in these regions where ice is climatologically thinner. So on to the advection and deformation terms. If we think about this with those currents in mind again, the Beaufort gyre, BG, is advecting thicker ice from north of the Canadian archipelago into the Beaufort Sea here, therefore increasing the thickness of the ice there. And then as it's carried around by the Beaufort gyre, the ice diverges and leads form, therefore decreasing the thickness in that region as this current picks up the ice. And you can sort of see almost a divergence effect in the vectors. When we actually calculate divergence from those vectors, it's the vector product was not meant to have divergence calculated with it. So the results, when you actually calculate divergence of those vectors, are not very suggestive of much, but maybe you can sort of see the hint of it with your eyes that the ice is diverging. The current is picking up the ice and diverging it, forming leads and fractures, decreasing the thickness in that region. We see that with the blue. And then the transpolar drift. All along the transpolar drift here, in the advection field, we have thinner ice being advected towards thicker ice. That manifests as a negative advection effect. That's what we can see the blue here. And as it's being pushed or advected towards that thicker ice, it's also ridging upon itself. And as such, we can see a positive effect of deformation due to the ridging along this path here. You might see some interesting looking things here east of Greenland, and very high advection values and low deformation. I have to say, that's going to require some further investigating what was going on here. Certainly we would expect most of the ice that crosses through this gap here, we call that the Fram Strait. Well, we don't, everyone does, that's what's called the Fram Strait. Then any ice that comes through that region has been advected there. So we would expect to see high advection, which we do. But I'm not totally sure on what's going on there yet. There might be something to with the observations. Not sure. But I'm pretty confident in the way that we described the Beaufort gyre and the transpolar drift here in the points that I just summarized. Okay, so an interesting question is, what is the dynamics relative to thermodynamics then? Which is contributing more in a particular region to the ice growth that the region experiences? So that's what we're looking at here. Dynamics relative to thermodynamics from the overall dynamics term, or like Eulerian dynamics, and the deformation or Lagrangian dynamics, what a Lagrangian observer would experience with dynamics on the right. And it's clear that some regions are certainly dominated by the dynamics. These look very similar to the plots from the previous slide, because the thermodynamic normalizing quantity here is fairly consistent across much of the Arctic, so the patterns look very similar, but we can see in these regions north of the Canadian archipelago, there's greater than 2 times the dynamic effect than that of thermodynamics. So I would say that means that that region is dominated by dynamics. And in these same regions and in portions of the transpolar drift, when we look at the deformation term or Lagrangian dynamics, we also have twice the importance of thermodynamic growth manifesting in dynamic growth. So there's a lot going on here. There's a lot of dynamics contributing to the ice thickness in some of these regions, which I think is an exciting result to start to understand. So then back to the mosaic studies that I mentioned at the start of this chapter. That's really the only work that is out there that we can quantitatively compare our results to. So what we've done here is the first of those 2 studies I showed was Koo et al. 2021. That was the one that used ISAT-2, so that was the one that was on a satellite scale. I've compared what we found for that same 2019 to 2020 winter along the exact same location as Mosaic. I went through in our data, my data, and pulled out the location of Mosaic at each time step. And what we have here is cumulative growth on the vertical versus time on the horizontal for dynamics in blue. We can see that this is a sort of a variable experience, as early in the season we have dynamics increasing, then decreasing the thickness, then increasing, then again decreasing, then through the winter, blue line, increase again pretty consistently to a peak here, then dynamics again decreases the thickness, maybe some fracturing going on in that region. And thermodynamics in the orange, very steady growth, as expected. It's cold, so the ice is going to grow. And it's a very steady, fairly consistent growth over time. And then total in green, it rises with the thermodynamics, but it follows a pattern of the dynamics. And then the dotted red, dashed red, is the ratio between the two, and the red triangle here is the ratio between the two found by Ku et al. In 2021 for the Mosaic study. So this is pretty cool to see that our studies, that is a 10-year climatology across the entirety of the Arctic, pulling out more localized results from the Mosaic study over a singular season along a singular drift track. The results agree fairly well. I think the Ku value is about 42%, we have about 48. That's, you know, this is the one way that we can kind of anchor the results from our work to what's out there. And that is encouraging to see. Okay, so a couple of conclusions from this chapter. This is the first basin-wide Eulerian sub-seasonal temporal resolution and long-term observational data set of dynamics and thermodynamics. I used slice and cryosat 2 to estimate dynamics as a residual. Slice was used to calculate the thermodynamic growth, and cryosat 2 was used to calculate overall growth. In the Beaufort gyre, we have negative deformation and lead formation or fracturing. In the westward leg of the circulation, in positive deformation and ridging along the eastern Siberian coast and the eastward leg of the circulation. Transpolar drift is characterized by negative advection coupled with a positive deformation and ridging along the drift track. And in some regions, dynamics accounts for twice the growth that thermodynamics does. And our results agree well with and expand upon existing studies. Okay, so in chapter 3, we'll return a little bit more to the motivation slides and get back to climate models and start to understand, where we can look to improve the dynamics in climate models, and ask the question, how well do global climate models represent these thermodynamic and dynamic sea ice effects from chapter 2? So hey, we got the governing equation here again. Might not be a surprise to learn that sea ice models solve this equation. It goes back to a lot of the same foundational studies that formed sea ice modeling, and most of the progress since that time has been how best to actually go about solving these terms. There are all kinds of really interesting, really awesome mathematical techniques that you can use that modelers have used to model both of these terms in order to model sea ice thickness. And they actually output these two terms as standard results from the global climate models, as well as smaller, more localized models, which makes a comparison between the observations from chapter 2 and the model results fairly straightforward. So that's what we've gone ahead and done. In the following slides, you'll see a comparison of monthly mean tendencies to monthly mean thickness tendencies of thermodynamics and dynamics to the observations from that same time period, 2010 through 2021. So the models that have been included, many of us are familiar with these, but I'll briefly go through them. So we have the NCAR, Community Earth System Model, Large Ensemble, CSM1. That consists of 40 members. This uses the SICE-4 sea ice model component. So SICE is the Los Alamos sea ice thickness model. It's a leading sea ice model that forms the component. The fourth version of that forms the sea ice component in CSM1. We also have the CSM2 large ensemble. CSM2, of course, includes various improvements over CSM1 and includes a larger ensemble population of 100 and an upgraded sea ice model in SICE-5. Then these next two are a little bit different. The CSM2 OMIP2 is a contribution to the OMIP program, meter comparison program. It is a fixed ocean and sea ice run. So what that means is that rather than having the ocean, the sea ice, and the atmosphere models running together, coupled, the atmosphere component is replaced by a reanalysis. So the intent is for the ocean and sea ice components to maybe more closely follow what actually happened via the forcing of the reanalysis. In this case, the JRA55 reanalysis. This one is only available from 2010 to 2018, so the comparisons with CSM2 to OMIP2, just be aware, 3 of the years are missing. And then pile mass, which is a sea ice thickness model reanalysis is the best way to think about that. It includes the thickness and enthalpy distribution and parallel ocean program models coupled together. Similar to CSM2 OMIP, this is forced by reanalysis and observed satellite data. So it's forced by passive microwave sea ice concentration data set and the NSUB-NCAR atmospheric reanalysis, various variables from that reanalysis. I don't have them listed. And sea surface temperature. Pile mass is often used, Jeff mentioned sea ice thickness observations. We don't have very long-term observational data sets with a lot of confidence for sea ice thickness observations. But oftentimes pile mass is used sort of as a stand-in as an observation. It's not an observation, but it's a model reanalysis forced by other reanalyses that forms, works as a stand-in as observations for sea ice thickness over a longer term. So right into the comparison. So model dynamics first. We have CSM, 1 large ensemble, 2 large ensemble, the OMIP, and pile mass. We have their mean wintertime model dynamics across the top for all 4. Then at the bottom for all 4, we have the model minus the observations. So where you see red, the model has overestimated the effect, and blue, underestimated. The black dots, I know oftentimes this means significant results. It's a little misleading. I'm not convinced when I submit this that that's the way I'm going to show this, but the black dots show where the ensemble range, remember the large ensembles include numerous model runs, 40 in the case of CSM1, 2 large ensemble, 100 in the case of CSM2 large ensemble. The black dots signify where the observations lie within the range of those ensembles at those locations. And that doesn't cover a whole lot of area in either of those large ensembles. And all 4 are very similar, where the dynamics are underestimated in the central Arctic, where we see blue, central to the plots, and overestimating dynamics sort of in these peripheral regions. I would say this is maybe the westward leg of the Beaufort Gyre, and kind of over here, which I would say is where the transpolar drift originates. Remember those 2 currents, those 2 predominant sea ice motion patterns that we saw a few slides ago. And interestingly, the 2 models that are forced by reanalyses, to my eye, don't look significantly better matching the observations than the free running climate models that are in the two large ensembles on the left. So then we look at thermodynamics. Similarly, as expected during wintertime, the thermodynamic growth is all positive. It's cold, it's growing, not melting. Fairly consistent spatially across the Arctic for the two large ensembles, especially. In the two reanalysis forced model runs, we have a little bit more variation, which is not unexpected. But then if we look at the pattern, again, model minus observations in the bottom row, it's sort of a flipped relationship from the dynamics, sort of out of phase in that the central Arctic, when it comes to thermodynamics, the models are overestimating the thermodynamic effect. And in these more peripheral regions, underestimating the thermodynamic effect. Similarly, very few regions, the observations are encompassed by the ensemble range. And again, same story for the two reanalysis forced model runs. Although maybe a little bit better, there might be a way to quantify some of these differences, but maybe not significantly enough that we would say there's much of a difference here, across all four. So then we can sum those two changes. Thermodynamics, yeah, John?
On the prior slide, James, does that give you confidence that the models know how to grow ice thermodynamically? Because if they're getting the thickness wrong, because the dynamics are wrong, but they're growing in response, they're excessively growing ice by thermodynamics. Isn't that what you expect?
Well, if this next slide might sort of, could you rephrase that question? How about
Yeah, what occurred to me was in the slide even before this, when you showed the dynamics and the CSM models, where you're not piling up the ice along the archipelago, and consequently the ice is thinner there, is my guess. Then that makes it more likely that you'll grow it thermodynamically. So that relationship seems to be borne out in those two model simulations. So does that allow you to say, with a little more confidence and a little more specificity, it's the dynamics that's a little bit off, not the thermodynamics?
Ah, I see now. Interesting. I hadn't kind of gotten to that conclusion, but if I could rephrase that a little bit to confirm I know what you're saying and use my next slide to do that, here we have total change, where the ensemble range, the observations are encompassed by the ensemble range in far more regions, and the differences are far less. So the sum of the dynamics and the thermodynamics is much better. And what you're suggesting, and I think I follow and I would agree with, the dynamics being underestimated in these regions at a given time step leaves the thermodynamics to counteract that difference, given that the dynamics is leaving the ice thinner.
Yeah.
And contributing to a higher thermodynamic growth rate in those regions. Yeah, I mean, that would make sense. And, the way I think you first phrased that is, do the models understand thermodynamic growth better than dynamic? I think that's probably quite true.
Okay.
Yeah, I think that's probably a logical flow of what's happening. Is the dynamic components could use some improvement, and the opposite is true as well in these other regions. Just reversing.
Yeah. The polarity is different.
Yeah, sure. I think that's probably true. I mean, so to kind of keep going on that line of thought, the total change, I won't go through, well, maybe I can. I mean, total change on the top, sum of dynamics and thermodynamics. We have the model minus the observations of total change at a given time step on the bottom. I would say all four models do better with total change. More area, as I said, covered by the ensemble range, enclosing the observations within its range. CSM2, maybe not quite as good as CSM1, which is interesting. It has been noted in literature that there's some interesting things going on with CSM2 outside the scope of this particular study. But yeah, to go kind of on John's point, maybe what's happening is dynamics needing improvement, leaving the thermodynamics the word I'm looking for is off the tip of my tongue, but counteract those differences, leading to an overall thickness change that's a little bit more accurate.
Compensate.
That's the one. That's exactly the word. Compensate. Thank you. So, chapter conclusions. We used observational estimates from chapter 2 to create the first thermodynamic and dynamic component comparisons to models. We have underestimated dynamics and overestimated thermodynamics in the Central Arctic, overestimated dynamics and underestimated thermodynamics in the westward leg of the Beaufort Gyre and where the transpolar drift originates. All these models exhibit more accurate total growth than individual dynamic and thermodynamic processes separate and need adjustment for more accurate projections. To John's point, likely more urgently to the dynamics component, which may be sort of driving what we're seeing here. And the last 2 points, so similar results across all four, even the reanalysis forced models. And you know, the model architecture for the sea ice components of these models are very similar across the board. It's outside of the scope here for me to kind of describe them, and it's really maybe sort of outside of my knowledge at the moment, but it's based on a lot of the same sort of assumptions and model architecture. So it'll be exciting to see, you know, if these results are meaningful, what kind of adjustments might be able to be made to the models to improve the dynamics components. Okay, so time is flying by. Summary and next steps. So chapter 1 was a thermodynamic sea ice thickness growth rate satellite retrieval. We found there that SLICE is an effective retrieval of sea ice thermodynamic growth. In chapter 2, we used SLICE to answer the question, what is the pattern of thermodynamic and dynamic sea ice effects in the Arctic on a large scale, temporally and spatially? We found that dynamics is increasing the thickness north of the Canadian archipelago and eastern Siberia. The Beaufort Gyre, we have lead formation and fracturing in the westward leg and ridging along the Siberian coast and the eastward leg of the Beaufort Gyre. And the transpolar drift, we have negative advection coupled with ridging along the transpolar drift. In chapter 3, we use the observations from chapter 2 to ask and answer the question, how well do global climate models represent these thermodynamic and dynamic sea ice effects? The dynamic and thermodynamic fields exhibit opposite differences, summing to a total sea ice thickness change that is much better than the components individually, likely driven by dynamic component issues. You know, there haven't been a lot of observations of this kind of thing yet, so it's you know, the models. I'm not disparaging the models in any way. This is an exciting area that we can make progress with new types of observations of the dynamics component. Okay, next steps. I think there's a lot to be found in the observations from chapter 2. There are all kinds of patterns that can be investigated. What kind of atmospheric conditions lead to certain patterns in the dynamics? What kind of, you know, so there's the Arctic oscillation that affects the location and strength of the Beaufort Gyre. What does that mean for the dynamics? I don't know. I've looked at some of the data. I think there might be something there, but I think that's a really exciting line of inquiry. And all kinds of other patterns like we looked into, you know, whether even more localized storm events, more localized you know, yearly differences, that kind of thing. And then particularly interesting too would be a longer term study. We would need a longer term thickness, sea ice thickness product to do that. Remember the growth calculation SLICE requires an initial condition H. So we need a overall thickness product to drive all this. And you know, there really isn't, like I said, a great product for that yet on a longer scale beyond the crosshead 2 10-year period. So we really would need a longer term thickness product for that. There might be some of that coming with passive microwave based data. Passive microwave data is available back to the 80s. So if we make something like that work, that might allow us to have a longer term study and start to find trends. You know, one of the big questions is, what is happening to sea ice dynamics longer term in a changing climate? Do we have a greater dynamic effect or a lesser dynamic effect? As sort of a discussion in literature. We don't know. So that would be an interesting question to answer. And then, of course, compare those trends to models. What models that we're rightfully basing decisions off of are the trends that these models represent accurate, and what can be done to improve them. So this is the end. Here, there's got to be a better way to do this, but I put all my references on this slide. So find what you're looking for if you are looking for something. But yeah, I don't have any acknowledgments or thank you slide, but I just want to thank everybody. I thank my committee in particular. There's the timing coming back. My committee, my advisors, Tristan, Jeff, and Yinghui, have been wonderful. It's pretty wild to think that this is the end. I don't know. We'll see what happens after this. But no, that's not. We're approaching at least the end of my graduate study, which is very exciting. So thanks to everybody, and thanks to my wife Eliza. There, I did it. So thank you all. Questions?
You want to take over, Tristan?
Or you could maybe
Okay.
just
I got it.
drive this.
You got it.
We'll be the MC. Oh, yeah.
Can you explain more? I guess I'm trying to understand the very basic question of what is advection in sea ice. Because in advection you would need a down gradient transport. And how do you down gradient a sea ice where you have, say, 2 parts on the left and 0 part on the right, and then are you gonna flip the ice in half and then transport that?
No. So if I understand your question correctly, if we have, so one parcel is a meter thick here. Next to it, we have a parcel that's 2 meters thick.
Right.
So, I'll just escape out of this. The current that is driving the motion of the ice has really nothing to do with the thickness of that ice. So the gradient of the thickness of the ice isn't driving the current, but what might happen is the current will move, this 1 meter parcel out from its location,
Okay.
and the 2 meter parcel into its location. So the effect there has been a 1 meter increase of the sea ice in this location by advection. Is that? Maybe not.
Yeah, it kind of makes sense. But
Kinda?
It feels like more of a Lagrangian than Eulerian. Right?
Well, so if you're using a grid, an Eulerian grid for this, if the grid in question was the grid that started with the 1 meter thick ice, that 1 meter thick ice moved out, a 2 meter thick ice parcel moved into that Eulerian grid box, then the effect of the sea ice thickness in that grid box has been 1 meter per time. It might be a little bit different, the terms, the way I'm using it, they might be a little bit different than certainly atmospheric dynamics.
But you're tracking ice, which is Lagrangian.
Sure, I mean,
What you're looking at is a certain spot, which is Eulerian.
yeah. I mean, there's certainly both. There's Lagrangian and Eulerian effects going on here. Sea ice, by nature, is just Lagrangian. I guess, so would things in the atmosphere be. But we just, lay a grid over it and assume, that there's a consistent thickness in that grid box, and whatever effects on that thickness in that grid box are occurring, whether it be advection, whether it be deformation through ridging, we assign a value to it. Yeah, I think good question. I'm happy to talk more about it too. Yeah.
So I know that in CESM and in most low resolution models, there's a problem with resolving how the ice is moving through the canyon, like the straits in between the islands. And you show an advection term that's lower than it should be. I'm wondering if you think that if you allowed enough sea ice to move through those straits, that the advection term, like right now it just looks like maybe the advection term is lower because the ice doesn't have anywhere to go, because in the model the orography is not correct.
Yeah, that's interesting. The movement of ice through the islands, even from a observational standpoint, like the motion vector product, doesn't have that either. I think it's generally accepted that most of the ice just piles up there, but yeah, that's interesting. In the the ice motion data set that I'm using for the advection, should be relatively accurate even north of the archipelago. But a lot of the basic sort of like material properties of ice is sort of a question. So like, to what extent does the stresses within the ice allow it to move through the islands? I think that's certainly a very open question.
Okay.
And yeah, I think that would certainly affect the dynamics in that region. Yeah, an area for investigation, I would say.
I guess a follow-up thought
Yeah.
then, if we don't have very good observations, do you think it would be worthwhile to have a campaign that goes out and tries to get really solid observations of how much ice is actually moving through this region and at what times, and et cetera?
I think that would be very worthwhile. It would be extraordinarily expensive given the extreme conditions. I think that's something that certain folks would be pushing for. The mosaic in itself was wonderful. The utility and worthwhileness of something like that is kind of obviously above our heads. I think so. Yeah, I think it'd be very expensive, and I think that would be great to do. It's also wintertime, so it's super dark and cold. And I should also note that there are improvements on a shorter time scale to these ice motion satellite products using the infrared. Jeff and you could talk about that better than I, but I know that, again, not for as long a time period, some infrared, smaller spatial resolution motion products are out there that might hint more at what's actually going on there. Yeah, good. Hey, John.
I recall that somebody that was a professor next door, early in his career in the 50s, went under the Arctic ice sheet in submarines,
Sure.
measuring the thickness, Clarence Clay. Is there some sort of ground truth that you've had comparisons in a detailed way of the ice thickness with something other than the remote sensing?
So there have been, upward-looking sonar from submarines is what that would be. And, as you can imagine, the data from those campaigns are far more sparse than a satellite, obviously. It's not news to you. And some folks have gone through and tried to splice together some of from the 50s that, along with the satellite data sets. I think they're just not quite spatially and temporally broad enough to be sort of, it's probably something I can incorporate, but it's just obviously the spatial and temporal scale of using those is a little bit more complicated. Ruger. Yeah.
That was a great talk. I have a more basic question. I think you addressed it at some point. Is that, does it still matter in this results what your sea ice concentration was? I know that people sometimes tend to remove the 15% like the marginal sea ice because it's subject to your observations. But when you're talking about sea ice thickness and dynamic and thermodynamic growth, if you consider thickness as a variable, can you now incorporate that 15% sea ice, or you still have to remove that because of the bias?
So I was able to go up, well, I removed even more. I require 95% or greater sea ice thickness. So that, that eliminates things like the effects of storms, for instance, which might be kind of what you're thinking of.
Yeah.
I really wish, and and the reason for that is just that the open water interferes with the passive microwave signal.
Mm-hmm.
And there's been some suggestions to correct for that. Like if you have a decent idea of what the emissivity of the ocean is at these wavelengths. But that starts to get a little iffy. There might be a way to do that, but I don't know at the moment. we're at 4:30, but Ian, you, yeah.
Yeah, just one
Yep.
question. For all these figures, you're using trends throughout the whole wintertime season. I'm wondering if you can comment on trends at the start, at the end, and at the end of the season, such that a change in divergence of ice thickness will lead to a later on trend in infection in the same region.
Yeah, I just today pulled out the seasonal cycle slide. I broke this out by month, and that would have helped answer the question. But I have not investigated yet what early season differences might mean for later season. That's very interesting. There are seasonal trends in the observations. I think that's another exciting potential line of inquiry with this data. Good question. I wish I didn't pull that slide out just this morning. But anyways, it's in the paper.
Great. Good plug for the paper.
Yeah.
So I just wanted to ask the committee members to kind of stay close, take a 5-minute break if you need to. But I think, James, we're meeting back in here, right, for the closed door part?
Yeah.
So besides that, if everybody will join me again in thanking James for a really stimulating